Welcome back. We'll continue with supervised learning from 3D or in 3D. In this part, we'll look at three main things that are kind of interesting, and of course, there's a lot of work here. First, we're going to look at how do you learn useful abstract features from 3D representations. Then we'll look into how can you use unsupervised learning and also take advantage of the 3D structure of the world to obtain things like depth of the scene and ego motion and your own ego motion as you're moving into the scene. And by ego motion, I mean motion of a vehicle in the scene. And then lastly, we'll talk about learning from again videos where you can use the ego motion to build very useful features. So let's first talk about 3D representations. So here the idea is if you have 3D data, an ordered set of points, for example point clouds, how can you represent the features on these point clouds so that they're useful? And they could be potentially useful down the road for things like registration, matching, and so on. So Corey, Zhu, and Coltoon recently came up with this nice, interesting approach in which they take 3D point clouds, and for each point in this point cloud, they build a high-dimensional 3D representation, and they learn in an unsupervised way the lower-dimensional compact feature representation, which can be used for other tasks. And so, if you have a point in 3D, you can parameterize it by many, many ways, and the way they choose to parameterize it, here is an example in 2D. And you have here the curve that you see is, let's say, your manifold for 2D right now. So they built histograms where you would partition the space radially in 8 chunks, and you would also partition the space building smaller, medium-sized, and larger concentric areas. So then you would build something like a histogram of how many of the points in this local neighborhood of this point cloud fall in this histogram. So for 2D, this representation is very simple, right, and easy to understand. This representation builds a 24-dimensional vector, and if you build an analogous representation for 3D, it will be order of 2,000-dimensional vector. And of course, you can use this 2,000-dimensional vector to try to match, to register, for example, two point clouds and so on. However, what this work is aiming to do is to build a more compact and more useful, to learn a more compact and more useful lower dimensional representation to do the same task. So the way they do it, they would like to build a lower dimensional embedding, and in order to build a lower dimensional embedding, you have to define which points should have the same representation and which points should have different representation. What they did is they used some training data in which the point clouds are, the registration between the point clouds is known, and you can obtain this data artificially, or you can have it. For example, you can have a point cloud and then rotate it, translate it, and so on. Maybe perturb it, add some noise, and etc. And now you would want to use this to just sample features and learn a better embeddings. And so suppose here you have 2 point clouds. One is shown in black, the other in red. And for each point here, you want to determine which of the other point counterparts should have similar representation to you and which should have different. And so basically the idea is simple. Things that are very close after these are registered well, things that are very close in your local neighborhood should kind of preserve the feature representation, should be similar. So in the lower dimensional space, you will add a loss to make them closer, and things that are farther, they need to, in the lower dimensional space, to map to things that are farther there. And so usually people use triplet loss or some variations of it for that purpose. And so after they learn this representation, as you can see, it can be done with supervised data, but it can be easily done with methods similar to the ones Carl mentioned, of having data that you already use and just either rotate it or add some noise or do something to it so that your supervision is fulfilled. And so an interesting outcome of these newly learned features is that they actually perform very, very well. So if you compare here on this graph their precision versus their dimensionality compared to other known features that work in 3D, you can see that these newly learned features, you can learn any dimensionality you want, but ranging between 12 and 32, for such a small compact representation, you actually have much higher effectiveness of these features. And so I think this is a very interesting result of how you can take 3D unstructured data and kind of learn to represent it in a much better way and use those features down the road. And so they exemplify their work with several tasks. So for example, here we're showing registration tasks. You have two 3D point clouds that are actually very big. They're made of many, many points. For example, the smiling Buddha is what is called. The first two rows are the two different point clouds. And you would like to register them by using those features. And so they show that previous methods have much higher error in doing that, whereas if you use these features and if you see the scale, their errors, their registration errors, they still exist, but they're much, much smaller. And same for the other C at the bottom. And also another way to visualize what are these features actually doing, or are they semantic or anything like that. So what they did here is that their feature representations, they now embed it in a three-dimensional space and then color-code it according to that. They just wanted to see if similar colors correspond to kind of similar shapes in this point clouds. And these are, again, two different point clouds. This thing is called smiling children, laughing children, or something like that. And then you can see that these features are also trying to get to things that are kind of similar in their local shapes. Another interesting work of trying to use the 3D as kind of inherent knowledge for unsupervised learning is of Chuis, Bilen, and Vidaldi. So what they are trying to do here is to learn a set of spatial features, let's call them landmarks, to not mix it with the features we've been using all along, landmarks within objects. And the input here is a set of unlabeled images. For example, you have a lot of images of cats, or a lot of images of faces, and you would like only from this data to be able to find, are there any special landmarks that they're kind of consistent, no matter if I change the person identity, or if I change the cat, or if I change the viewpoint, and so on. So this is basically landmark learning in a supervised way from a set of unlabeled images. And they do a lot of the tricks that we have already heard. For example, one way of doing that would be to take these images and rotate them with known transformations and use these and learn towards these transformations, and this is how they learn these features to be the same. So the assumption is that these features should have undergone their distance in the new feature representation should be they should have undergone the same transformation as the image had undergone. But the underlying idea, so I'm mentioning this that they're doing some 2D rotations, but the underlying idea is that it comes from 3D. That actually these features, if it's two viewpoints of the same object, or even if it's two birds that should have the same landmarks, they actually, these landmarks, like their eyes, their beak, and so on, they will map to the same 3D kind of, the same 3D representation, or the same 3D point, and from which then you can find the projection. So in their work, what they're doing is something along the lines of they get a lot of images, then they transform them, in this work mostly in 2D. And when they transform them, they know what transformation had happened. And they built a network that's a Siamese network for the image and its transformed image. And each of these Siamese networks is supposed to output a set of landmarks. And because they know the transformation, they're applying a loss so that to be able to match these landmarks together. And when they do this, they're able to recover the landmarks for things like shoes. So you can see it matches well on the tip of the shoe or on the back of the shoe and so on. And they're able to also learn landmarks in a supervised way for things like faces and also tap faces and things like that. And the same team has a follow-up work in which they show that this is not limited to kind of viewpoint changes and mutations, translations, but they showed some more work with deformations where they can use, for example, the optical flow to know where things went and use this as supervision. And another interesting work that is also not using supervision but has very interesting outcomes for things like robotics is finding depth and ego motion from the RGB image, RGB video. So in order to do that, you can't just have a video. You need a video where you are actually moving inside to be able to learn ego motion. And again, ego motion is the motion of the vehicle that's moving in the video. So the pioneering work of showing that this is, can be done with neural networks was last year at CVPR by Pierre et al. The input, as I said, is a sequence of videos, and the output is the depth per image and ego motion for 2 consecutive images. And so here is the formulation. They would be building a nonlinear approximator from the target view to the depth. It's a neural network. And then from 2 views, there's another neural network that's supposed to give the pose. And the pose here is encoded as a rotation and translation. And so here is an example of what these networks look like. They're very typical encoder-decoder type of networks. And the ego motion network is much smaller because you don't need as many convolutions. So all these blocks are convolutional. And so here the idea is that you would have, suppose I have something to predict the depth of the current scene that corresponds to the current image. Then, and suppose I have another thing that tells me if I take a step, what is my motion? So if I do that, I can take the depth and generate a point cloud of where things go in the 3D. And then rotate it according to my ego motion. And when I do that, and if I project it back to the image space, I should obtain the next image that I would see after taking this ego motion. And using this constraint, so as you can see, this constraint is entirely coming from the RGB space. Although you're taking it to 3D, you're saying, I would be learning depth, moving the point cloud, but then I'll project it, and then I will impose constraints on the RGB space only. So with only that type of learning, this is called photometric consistency because you're doing, you're penalizing errors in the RGB projections. Then you should be able to use this as supervisory signal to learn your depth and ego motion. So things are a little bit more complicated than that. You need some sort of regularization in order to learn such a thing, and people usually accomplish this by adding some smoothness losses and other things like that. But the overall idea is that you would not need any depth sensor to tell you what the actual depth is, and you would not need a GPS to tell you where you move between these two points. So now, the same kind of thing could be learned using stereo. If you can learn it from a single frame, if you can learn your depth and ego motion by moving, by using only a single monocular video, you can possibly do even a better job by using stereo. And Goddard et al. Showed that with stereo, actually, you can produce much higher and better quality. So here the only difference is that you have, instead of looking at the image from one frame, you're looking from two frames. So twice as much information, so to speak. And they have, and their algorithm is, the idea of their algorithm is to be able to use both cameras, left and right cameras, to be able to impose the same consistency. So here the trick is that only the left image is used as input at inference time, because you would like to only use stereo during training but test in an ocular setting. So the input image, let's say the left one, is learning two networks, so to speak, or one with two joint outputs to predict the disparity, which is, you can think of it as 1 over depth with coefficients depending on the camera parameters. And it's learning disparity with respect to left image and with respect to right image, and then you're using the actual left and right image to impose consistency. And they showed very good quality results. So if you can see at the bottom row, this is also CVPR 2017 paper. And you can see that the results are much higher quality, and also they have uncovered kind of very good 3D structure of the world. So this is also very interesting work. So now the question is, do you need stereo during training in order to learn good quality depth? And here's some new work that will be presented here at CVPR of our own that uses, again, monocular video to uncover depth and ego motion, but we also impose 3D constraints. And so the idea is, in addition to all the losses I've talked about, the photometric one and depth continuity and so on, to also impose a loss on the 3D point clouds. And the way it works is you have this, from each frame, you generate depth. That's still a learnable thing because you're learning it, right? Then from the depth you can generate a point cloud. Then the next frame can also generate its own point cloud. And then you know the ego motion between these two, or you don't know them, you have a network to learn them. And so you can use the ego motion to kind of rotate this point cloud to the next one, and the next one to this one. So doing this in both directions. So when you rotate these 2 point clouds, they may still be misaligned. So what we do during training is you take the misalignment. So if they're misaligned by some sort of rotation and translation, we use this as backpropagating signal to improve your own estimates of your own ego motion. You must have an error there, if the point clouds mismatch by this much. And if the point clouds are different in how they match point by point, that means that you must have an error in your depth estimation. So we use it as backpropagating signal to improve your depth. So instead of using stereo, we kind of have this 3D constraint used during training. And again, we use ICP to align them, and then these backpropagating signals to get the useful signal. They're not simple to implement or accomplish, but the good thing is that they're only needed during training. So you need only this 3D information during training, and you can use the learned networks with a single image during test. And so here we see that if you plot the losses where you don't use the 3D loss versus when you incorporate it in learning, you can see that you have much better performance, and you also have much better stable training without overfitting and things like that. And so here is our results in the green box, and on the bottom is the ground truth depth, which is not used. It's only visualized for comparison. And this is the ground truth that came from the laser sensor for the QT data for which we trained here. So you can see that our results are also very good and very crisp, and can find good geometry in the scene. And if we compare in terms of absolute error, so approximate numbers here, but the first work I showed of Zhu et al. In terms of error is 0.21, and the stereo work is 0.14, and if you use this trick without using stereo, you use this 3D alignment, you are at 0.16. So it's not better than stereo, but it is getting closer. And so lastly, let's talk about whether your ego motion or the way you move. So we already saw that ego motion is learnable and useful. So now it's going the other way around. If I know the ego motion, so somebody told me the ego motion, for example, some GPS signals or something like that, can I learn useful and interesting features? And what can I do with those features? So this is the work of Agrawal et al. And there's also some related work of Jayaraman and Raman. But let's talk about Agrawal et al. That's called learning to see by moving. So here the idea is simple. You take two images, run them through a Siamese type of network, and what you're trying to obtain at the end is you're learning the transformation that had happened between these two frames. And Carl already showed you good examples of you can obtain very useful transformation by rotating things, or if things are shuffled, to unshuffle them, and so on. So here the idea is very, very similar. And in this case, I think the authors first started with taking MNIST and just rotating it in plane and so on, and trying to learn the transformation. So an interesting thing happened when they learned it on the Kitty data set. It's the same on which we learn depth and ego motion and so on. It has a lot of sensors. It has ego motion. It can give you smoothed ego motion by using the Kalman filtering over GPS signals and so on. So it's a pretty good ego motion, let's say. So if they learned this task on predicting ego motion from two consecutive frames, they obtained the filters that you see to the right. And they have two data sets. One is the Kitty, and another is another similar type of data set. So you can see first that the filters that are learned just by this simple task are actually very close to what you would learn from a supervised task. So then they use these features, and they actually use, as always, the feature representation at the end of the learning, and as their feature embedding. So when they use this feature embedding, now they're trying to say, what if I take this feature embedding and now use it as a pre-training for a classification task, for example, for ImageNet and stuff like that. So what they showed was something very interesting, that actually these features are pretty close. They do not beat the fully supervised learning approach, but they are pretty close on fine-tuning on this task. Another very, very interesting thing is that they show that if you change the task, which typically is a classification task of multiple classes, and if your task is something like tracking or if your task is ego motion prediction or something of this sort, then they're finding that their features are actually even better. And not only that, but in their training setup, because Kitty dataset is kind of very small volume, they have trained AlexNet on the same volume of images, and they have trained AlexNet on 1 million images, which will be the bigger and better version. And they show that on these 3D type of tasks, these features are even better than pre-trained features on AlexNet on 1 million images. So I think this is very interesting observation that basically says that depending on the tasks, some features, if they're learned within the same domain, they're much more adequate and much more useful and more interesting. And something to keep in mind, because we often, when we evaluate the usefulness of features, we often try to compare to a classification task. And so basically, they're answering this question in their paper. Is strong supervision necessary for good feature representation? And they say, well, not really. We saw that even for classification, our features are pretty good. They're not better, but they're pretty good. And they show that for specialized tasks, they can be even better than fully supervised features. And so that's it for this part. We talked about how you can use the 3D information to learn invariant type of features. We talked about how you can use your videos only to learn other interesting things like depth and ego motion. And we talked about using some things like ego motion to learn very useful features. And thanks. I can take a few questions now, and then we'll continue with the next one.
So you mentioned you use ICP in one of your paper, and you can do backpropagation with ICP. How do you do that? I think it's not differentiable.
Exactly, it's not differentiable. So this is approximately differentiable, and we use the ICP to match points. And we don't have a full gradient. We use an approximation of the gradient, but it still works reasonably well. So it is not a fully differentiable. It's approximate. That's a very good question.
So you need, I think, you probably need a good alignment at the beginning.
Yes, that's also a very good question. You do need a good alignment. We actually haven't tried it from the very, very beginning. We usually train with other constraints to a reasonable setup, and then we continue training with ICP. Both very good questions. Thank you.
I have one more question. So at the test time, I assume you would compute the depth frame by frame. Do you observe the flicking artifacts if you apply computer depth for each frame in a video?
Not really. You can see we have some videos up, and I had some video this morning. You can see some of the videos. They look pretty reasonable. They're not as good as stereo trained videos for this task. I think you're also getting to another very interesting question: is how do you combine and make a smooth prediction across frames, which is an open question and something to be explored.
Thank you.
Thank you. Okay, so let's move on to the fourth part, self-supervised learning for robotics. So here we'll talk about what is self-supervised learning and why is it important for robotics. Then we will discuss self-supervised learning for navigation and also online self-supervised learning in these settings. We'll talk about self-supervised learning for grasping, and in the final part of the tutorial we'll talk about using self-supervised learning for imitation and featuring towards zero-shot imitation learning and type and trusted networks. So first, what's the difference between unsupervised learning and self-supervised learning? Are they the same? We hope in both cases we don't use much labels. So what is the difference? So suppose you have this video of some things happening or somebody interacting with objects in the world. A supervised learning here would be human labeling what type of action this is, what's happening, what's the pose of the hand, where is the cup, and so on. An unsupervised learning from this video will be a lot like what we have talked about today, using sort of autoencoding or trying to do dimensionality reduction with certain constraints. For example, you can autoencode things into these images to be able to reconstruct them. You can add some priors or constraints and so on. And so that will be a purely unsupervised learning. Whereas self-supervised learning, especially in the context of robotics, will mean that you're going to be using some other constraints from the world. You may use one of your sensors as your own supervision. You may use some constraints that come from the 3D, from depth or time. You may use multi-view as your supervision. You may use a tactile feedback of how you touch things, what was the sensing signal there. So this is kind of the difference that I can define. And as you see, the lines are a little bit blurred. So for example, if I'm using ego motion as my supervision, is this self-supervised, is it unsupervised? So there is up to debate, but usually self-supervised is used in the context of robotics. Why is it important? We already went over some of this in the beginning. Supervision may be ambiguous or subjective or ill-defined, and maybe even impractical for robotics to determine all the pose and all types of things happening. In robotics, you have a lot of sensors, a lot of data. Things are complicated, lots of things. The data is very, very high dimensional. It will make sense to use some sort of unsupervised learning to be able to maybe find the useful components there or find the useful representation before trying to do any learning with robotics. And in the same sense, you would hope that these lower dimensional useful features will try to disentangle and uncover what really matters. We'll see in this tutorial that some of the methods can help improve the sample efficiency for some reinforcement learning algorithms. And this means that they can learn faster and reach good results. And we'll also see some online learning and adaptation in the context of self-supervised learning. And we actually start with that. We will talk about self-supervised learning for navigation. So a couple of things that really open up a lot of learning for robotics in the domain of autonomous driving and navigation, which a few years ago was mostly off-road, but also there was some urban driving too, are the DARPA Grand Challenge and the DARPA Lager Challenge. So the first one was for driving on dirt roads, and the last two papers are a couple of examples of learning with self-supervision for the Lager Challenge. So the DARPA Grand Challenge was a set of competitions in which the fully equipped autonomous vehicle is supposed to drive on a desert road unknown road and reach a destination as fast as they can. One thing that's a highlight here is that nobody has seen the course, and they don't know what the road will look like. Would it be more gray or dark or brown, etc. So they have to learn and adapt. And previously, I would say most of those systems weren't using much learning, but these challenges kind of pushed the teams to use more learning. And several interesting approaches came out of it. For example, Dalkham et al. And several others actually showed us a self-supervised learning in which they're using their their laser to tell them what is a road traversable and what is not. And their laser sensor is reliable until 15 meters, so this trapezoidal area. And then they have the camera, and the camera is learning what else could be traversable, and thus they can extend the range. And they actually show that this would really help them win the competition, because if they can see farther, they can drive faster. And so here are an examples. So in addition to learning self-supervised, so using one sensor to supervise prediction with the other, they also did update their learning parameters online as they go. And so, for example, they here are showing an example in which, in the beginning, they thought the road is more brown or pink, and then the grass is traversable, and then the grass on the side is non-traversable. But then, because later they were supposed to drive on this grassy area, that's the bottom row, and they now figure out that it is also traversable. Now the algorithm, in the top row, they still think that grass is not traversable, but then in the bottom row, now they know that it is traversable. So it had learned online. And they had some other interesting ideas, something like, you can think of it as the ring buffer in their learning space. So for example, if they use mixture of Gaussian, I think they did, they can let new type of terrains appear, and then they can forget about terrains that they haven't seen for a while. That is really adaptive to the terrains. And so here are some more examples. And as you can see, in some cases, they see very little reliable laser sensor. In parallel, or maybe a year later or so, there was the Darper Lager challenge that distributed this much smaller robot, kind of a feet tall, to 8 to 10 teams, and they get identical robot, which is already capable of driving and has the same software and so on. And that basically allowed each of these teams to build their own algorithms for building, smart navigation algorithms. And so here, very similar challenges. They're supposed to drive now off-road, and they have to avoid obstacles. They have to avoid getting stuck in a cul-de-sac. So this means that they kind of have to see again farther in order to plan more intelligently. So here is some of our work long years ago, again from the Lager challenge, that is very similar in flavor to the previous work I showed of Dalkham et al., in which here we're using the stereo, because this one did not have our lasers. A stereo will give you information of what's an obstacle and what is not, very short range, and you can use the information from color and texture to extend the range of how much you can see. And a similar idea of Raya Hatzel et al., this is from New York University, to extend the range, but now is done with deep neural networks, and note that this is in 2009. So they were one of the teams that really showcased that neural networks can be successful in this task. So here you have the input image, the traversability that stereo gives you, and stereo gives you, the depth, so you can now know how tall things are. And to the right, you can see after the deep net had learned what it now thinks is traversable. And you can see that it can effectively extend the range of how far you can see. And in addition to that, they're using also online learning type of technique in which they're learning their networks offline because I think they're still heavy and slow and so on. But they let the network adapt its last layer as it is working on the fly, which is also very, very interesting. And so here's a little bit of details. So first, in order to be able to apply the network, they try to find the horizon and kind of the ground plane and normalize for that. Then they have another neat trick that's shown here in the middle. They give their network patches, as far as I can tell. And each patch should say an obstacle or not. However, if they give a patch that's close by and a patch that's super far, they're at very different scales, right? For example, the close by, the far away may have a full tree, whereas the close by patch will have only a small, will be big, but will have only a small part of a tree. So what they did is basically they sliced the image horizontally, but using the proper horizon, and then they will normalize the patches according to how far in depth they are. So you can see these, I have to really look at here. So the first one is 4 meters to 11, 5 to 17, 9 to 34, and so on. They overlap, but it doesn't matter. They just are collecting training data. And then they give this training data, which is now scale normalized, so to speak, by using the depth trick. And they are giving it to a neural network. It's very standard, very typical Lunette-style network at that time. Was 2 convolutional layers and 2 fully connected, or 3 convolutional and 1 fully connected, and stuff like that. So you can see it here at the bottom. And so here are some interesting results. Again, they show input image, what you would have seen only by your reliable stereo sensor and what you could see by additional learning. And to the left, you can see how much time they can save by using this long-range planning. Because if they can see farther, they can plan better. So they can see that. So, for example, in the first run on the first course, instead of 300 seconds to complete the course, they needed 150. They also traveled much less distance, and also much fewer interventions. And actually, practically for these 3 test courses, they had no interventions when they used their learning algorithm. So let's see now how we can apply self-supervised learning in the context of grasping. Pinto and Gupta showed this very interesting way of collecting data for grasping and also for directly learning grasping. So far we have talked a lot about learning features that we can use later or help some other tasks. But this work actually showed that you can directly learn good grasp. Previously, grasping was done by either manually labeling potentially good boxes, basically like that, or some 3D alignment and kind of evaluation, very careful evaluation of potential grasp in simulation mostly. So here what Pinto and Gupta did, they had a bunch of objects, and of course the objects are spread out and so on, so this is probably done supervision, and they could be like maybe a little bit segmented so that you can kind of zoom into where they are, but I think nowadays you don't even need to do that anymore. And then they have the robot doing random actions trying to grasp. And if it happens that a grasp is successful, which in the beginning wouldn't be so often, then the robot will record that as a very successful grasp and keep this example as a successful grasp. And so here you can see on the right some examples like approach an object, execute a random grasp, and then verify if it is successful. And how do you verify? Usually there's different ways, but you can have sensing on the gripper, or you can also visualize, you can also verify visually if the gripper is closed or not. In some of the recent Amazon challenges, people are really using some of those techniques because sometimes the gripper can close over something that's very thin, and in this case, a visual feedback will be the only thing to tell you that has happened. Sorry. So this work was very interesting. They also generated very large-scale data without having any human labeling for grasping. And another interesting follow-up work of the same team proposed to improve grasping by adding an adversarial process. So, if you're trying to hold on to something and somebody is pulling on it, you would try harder, right? So the same applies to robots, seems like, and they actually implemented this by having two robots. One is learning to grasp by the same algorithm we just discussed, and another robot is trying to destabilize the grasp by doing a set of things. So, for example, it can shake the arm in several configurations, different frequencies, different angles, and so on. It can try to pull it or snatch it, or it can try to push the arm so that it can fall. So several interesting things happen out of this work. First, they observed that after training with this adversary in the loop, instead of just having grasps, they now have much more stable grasp. So you can see the top image shows grasp, and then similar objects, more stable grasp, which is great. But also they demonstrated that the grasping with adversary accomplishes much higher accuracies after the learning process has ended. And as you can imagine, in the very beginning, let's say after one epoch of adversarial grasping, the grasp success was not as good as it would have been without adversary. But after iterating 2 or 3 times, now the grasp success is much better than it could be done without adversary. And they also noted in their paper something interesting, that, for example, adding 6,000 of 5 or 6, I forgot, some 6,000 new examples of adversarially learned grasps is much more valuable than adding 3 times as many of normal grasps. So some examples are more important than others, which we know from hard negatives and so on. And here, the most interesting thing is that all of this can happen without having a human label anything, and it's just kind of self-supervising, using your own embodiment in the world, your own interaction with things and so on, and smart algorithms. And finally, we'll talk about imitation learning. So what is imitation learning? What do people mean by that? Imitation learning usually means you're observing something from a third-party observation. So somebody else is doing an action, and you're trying to imitate the same action in your own, with your own sensors, in your own embodiment. And so here, notice that the TV, so here the baby is imitating very well, right? The TV is not aware of it being imitated. So it's a passive signal. You can use a lot of things like videos, images, and so on for learning. And we believe that a lot of these, although it may not make sense, it actually you would learn a lot from just doing those kind of things. And also to highlight that there's also a learning from demonstration in robotics, which is different because demonstration typically means that you're doing it from the point of view of the agent. So demonstration means you may take the robot arm and with the arm demonstrate how a grasping should happen. It's in the same space. Or you are teleoperating the robot. It's in the same space. Whereas by imitation, a human may imitate in YouTube video how to cook, and you want the robot to do the same in with its own actuation and so on, different viewpoints and things like that. So what are the challenges of imitation learning? The big challenge is the correspondence problem and viewpoint change. As we just said, it's usually observation from a third party. So you need to have features and things that are invariant to that. Also, of course, big challenges are finding features that matter, that uncover the important things, and of course, how to scale and how to learn with ambiguities and stuff like that. But also it gives some opportunities. For example, it may help scale up reinforcement learning. For example, it may help it learn faster with smaller number of examples, which is referred to as a sample efficiency. And also in some cases, for example, in this task that's for door closing task, you may want to use reinforcement learning to learn to close a door. But then you need to provide a reward signal for that. And if the reward signal does not come from a human, it may come from other sensors. So for example, you may want to have a sensor that detects if the door is closed. That is fine, but it also may not scale as well as if you had some other type of supervision that you didn't need to do anything like that. And also, mutation learning can help you avoid these kinesthetic demonstrations, which need to be necessarily done from the point of view of the robot, and may be expensive. Recently, Deepak Pathak, Parsa Mahmoudiyeh, and Guangkao Ru et al. Demonstrated zero-shot imitation learning, which is very interesting to me. Their idea is, and it's actually very common for imitation learning to think of things that way, is to first let the robot explore the world, kind of learn representations and stuff like that. And then what differs in this particular work is that they're going to they're going to show imitation, a single imitation for a task, but they're not going to demonstrate the task being done. They're only going to demonstrate a set of states that they want to be accomplished. And this is a very nice way of formulating imitation learning because of the third-party problem. So if I'm to imitate, if I'm to demonstrate to a robot how to tie a rope, I would do it with my own hands. That would be different features and so on. So it's very hard to match those. So instead, they're only matching a set of states that they want to accomplish. Let's say here, step 1, step 2, step 3, step 4. And because the robot had played with the world, so to speak, and has opportunity to explore and so on, and can try trial and error until it gets to these states, there is still a chance to learn this very successfully, and this paper showed that it can be done, and it's actually very cool. So the way they do it, so here the robot is already doing the first step, as you see. So the way they do it is they first apply this self-exploration step that's also done in other works. And here the interesting thing is they would learn a different type of policy. So usually a policy would be given the state and observations and an action. What is the next state? And in this way you can learn a sequence of next state. What is the next state, right? you can learn a set of actions so that you can achieve certain states. So here they turn it around and they learn a neural network that, given a state and a final state, and is parameterized on theta, what action or sequence of actions could have taken the world from one state to the other. And to do that, they used a lot of they basically took the normal policy in which a lot of exploratory algorithms. They used a normal policy in which the robot observes the scene, right? Then takes an action, then observes what's the next state, and so on. And using those examples, then they can learn this next new policy they call goal condition state policy. And once they have it, and they first learn it for one step, and they learn it afterwards with an RMN to multiple steps to obtain multiple actions from one state to the other. And so then they demonstrated it for the knot tying task, and also for another task for the turtle bot, where the turtle bot is navigating in the area here, and the goals are given as a set of images of what the scene should look like when it reaches it. So you can see how the input image that the robot observes and the first state are very different. So the robot really needs to look around until it finds the image and so on. And using this technique, what the robot does is applies the learn algorithm and try to find the next state. And if it can't, it recursively, they have a kind of a small module in which they can detect that the state had not been reached, so a different image is seen, and then they reiterate they try to explore the world more until they get to the next state and so on. So this work is very interesting in the sense that you can provide very little guidance or very little supervision for this imitation learning. And another work on imitation learning, which is very interesting, is time-contrasted networks. So here we want to do imitation from third party, where a human is doing the demonstration of something and a robot is supposed to mimic it. The underlying idea is that you want to build underlying feature representations that are invariant to viewpoints and also learn about interactions of the world. So what the team does, Pierre, Sermanet, Lynch, Evgeny Chebukar, et al., is collecting a bunch of videos from two viewpoints that are synchronized. And these videos are of pouring or moving cups or putting things on top of one on top of the other. And you'll have two videos like that. So you would be learning a very typical triplet loss in which the same event taken from these two viewpoints at the same time should be represented by the same lower dimensional compact feature representation, whereas things away from it should be apart. And so they use the triplet laws. If things that must be similar are far, they need to be brought closer within a certain threshold, and if things are too close but need to be separated, they need to go beyond a certain threshold. And so with that type of learning, they're building this, let's call it TCN embedding. And then, using this TCN embedding as their main feature space, they're going to have a human demonstrate a task for, let's say, 10 seconds, and the robot is supposed to do the task. Self-supervised imitation. So notice here that we need this smart embedding of using different viewpoints, because you really are doing third-party imitation. You really need a viewpoint change to not matter. So here is an example of a task in Sim. Hopefully robots will be able to do dishes in real soon. So we're learning the embedding. And then here is one demonstration of trying to put, and when learning the embedding, it's not only moving things on the rack, it's actually lots of other things. So here is the demonstration you saw, and now the robot is trying to learn to do the same task. So this is still the learning process. So you would appreciate that it's actually, even in simulation and so on, it's actually very challenging to kind of hold on to it, know exactly what forces to apply and stuff like that. Okay, so here is the, so here is the learn policy, again the demonstration and the final learn policy. It's a little bit shaky, but it still managed to put the plates in place. Hopefully soon in real life. And so here we want to highlight that the whole learning is done without any labels and from these different viewpoints. And so now off to real world experiments. The team collected data like that with interactions in the world. And so here is a single demonstration, and the interactions were done both by a robot playing and a person playing, but there was no cross-robot to person examples at all. So here is the robot is trying to imitate this pouring action, and we're using granular media, these small points, balls, because you don't want to spill water around robots. So as you can see, it's a challenging task, and the team observed that the robot first, and I think they're showing kind of the good part of the learning, it first learned to move the gripper closer to the cup, and then learn the more finer motion of the hand moving. And so here is the learned task. So notice that this is a single video of less than 10 seconds, 9 or so. And so here is what the robot learned, and also the viewpoints are different. So here they're showing it from different viewpoints. The viewpoint of what the robot has and what the video is are different, and that's the point. So the way this learning is happening for both tasks, the simulated and this one, is that the TCN embedding is the only feature representation that is being used. So the robot is kind of using its image of what it is doing, and it's embedding it in this TCN space, and there, with only L2 distance, a reward is added saying that they should be as close as possible. So this is the reward signal for a reinforcement learning algorithm. So if you are to apply a reinforcement learning from scratch, that will be a really very formidable task, just because of the super high dimensional feature representation and so many ways to explore. And you would not be able to do it, directly with a robot from such a demonstration. So this is actually a key part of this work. And so here's some quantitative results in which they compared their embedding, that's TCN, and how successful. So here the curve shows how many of these, how much of the liquid was successfully transferred, or how many of the beads were not spilled. And then you can see that the TCN actually in the beginning is not as good, but gradually improves the performance and has a very good performance in the end. Whereas the other embeddings, the same setup, just different embeddings, including a single view version of this one, and also shuffle and learn, something Carl mentioned, they're not as successful for this task, just because this task is more attuned to manipulation type of tasks. And so here's some more performance comparison, again with shuffle and learn and single view TCN versus multi-view. So really the fact that the features are invariantly used is really helping, because it's a third-party observation. And the same work, actually, the team showed that it can be used for pose imitation. This sounds a little bit funny, but a person is trying to imitate some pose, and the robot is doing it with one of its arms. And they're actually doing the same TCN embedding. So here we have the TCN embedding is built. It's a little bit richer, where you have the robot observing itself from two views, and a person doing actions from two views. And then also, while the robot is observing itself doing some random actions, it's also learning a regression between what is the feature representation state and what are its joint angles, kind of its state. And because now it has learned that, it's actually now very easy to be able to imitate the human by using the same joint embedding. And so here's some more examples, and actually they have a web page with a lot of examples of this. In summary, we discussed self-supervision and why is it important. We talked about self-supervision for the purposes of navigation, as well as using online adaptation. We also talked about self-supervised learning for grasping, where you can directly learn grasping, and we also talked about adversarial learning and how it can make things much more accurate and better. And finally, we talk about imitation learning and using self-supervision for that purposes, and we talk about two algorithms, zero-shot imitation and the time contrastive methods. In summary from our tutorial, we hope that we've managed to convince you that using unsupervised learning is useful and very powerful, and that you can use it from in various ways, from on images or videos. You can take advantage of 3D structure, and in the context of robotics, you can take advantage of your own interactions or some other sensors or other constraints, and you can either build features for better supervision or help reinforcement learning do things faster and quicker, or you can directly learn outcomes as is in the grasping, or you can provide better features for other subsequent tasks. And thank you very much for your attention. We will upload the slides on our webpage, and I welcome questions.